Welcome again to this channel. In this presentation, we are going to talk about protection of PV cables and components in a PV system. All the discussions in this presentation are based on IEC standards. Figure 1 is a layout of components you are likely to find in a typical solar PV layout. All components in a PV system should be rated. This is to say conductor, disconnectors, switches, all should be rated. Now when we look at this diagram, we see on the left side we have the solar panels, two types of combiner boxes. So we have the string combiner box and sub-array combiner box. Essentially these two boxes will have protection devices installed in them in the form of fuse or MCB. As we move across the diagram from left to right, we see the string cables, then we have the array cables, then we have the DC inverter cables, and finally on the right we have the inverter AC cable. Let us now look at PV system cable sizing. And we take that PV cable should be of the size that will limit the overall voltage drop between array and inverter to below 2%. Now this depends on your standards. Now we look at these definitions, and these definitions are going to define some of the parameters that we're going to use throughout this discussion. So take note so that as we move along, then you know what they are. At this moment, let us look at some common overcurrent protection devices and then compare them. The three common overcurrent protection devices are fuses, MCB and MCCB. Each of these have their advantage and disadvantage. And at this point, we're just looking at a simple comparison between the three overcurrent protection devices. And we start with the fuses. And there are three types with the semi-enclosed fuse. This is a rewirable type. Then we have the cartridge, and we have the high rupturing capacity. What is known of fuses is that they're cheap, and when it blows up, it has to be replaced. The other type of overcurrent protection device is the MCB, or which is miniature circuit breaker. They are rated for currents up to 125 amps. And the standard rating for the DC type varies between these figures here, 1 to 63. These are the common types, but there are other manufacturers who make other sizes, other ratings in between these standard ratings. Comparatively also, we have the AC, because in a typical PV system installation, you'll have both the DC and the AC side. So also the AC side, we have similar ratings going up to 100 amps. And what we know about the MCBs is that they are reusable and more sensitive to currents than the fuses, but they are more expensive than the fuses. The third type is the molded case circuit breaker, in short MCCB, and these are manufactured up to 3500 amps. And the good thing with MCCB is that the trip current is adjustable, and they are commonly used for industrial and heavy applications. Let us take a look at what happens when a fault occurs in a PV array. In this diagram, figure 2, we see this layout of when there is a fault in this particular string here. Current will find it easier to move in this direction rather than go towards the load side. And this is because this path will have low resistance and current will choose that path. If the reverse current flowing into the string is greater than the reverse current rating of the module, then a protection in the form of fuse or MCB should be provided. The overcurrent may cause heat or fire along that faulty string. So to provide some initial level of protection, all modules are normally rated with a reverse current it can withstand by the manufacturer. To overcome reverse currents, a fuse or MCB should be provided if the reverse current flowing into the string is greater than the reverse current rating for the module. When a fault occurs, the maximum reverse current to be experienced is in the form of this equation here. And we are defining that N is the total number of parallel connected strings, and N should be greater than 3. and ISC is a module short circuit current. Now this case is that it is required that all these modules are of the same manufacturer and same rating. And we have another condition here that N should be greater or equal to 3. The thing is, where N is less than 3, say 2 for example, the bracket reduces to 1, and as such IRC becomes equal to ISC. So no protection is required. Where there is N is equal to 1, then of course this part reduces to 0. Then basically we don't have a circuit there. So we will not be discussing reverse currents. So to better explain reverse current protection, let us look at this example. In this case, we have been given that we have the module short current is 8.45 and the reverse current rating is 15 amps. So from figure 2, we see that if a fault occurs in sub-array 2, string 2, the total ISC will be that from the total 3 sub-arrays less the fault one. What we are saying mathematically is that total current is equals to IRC, reverse current of the module, and this is expressed as N minus 1 times the short circuit current of the module. And if we insert those figures, N is equal to 6 minus 1 times 8.45, which is the ISC, we get 42.25. And now 42.25 is greater than the module reverse current rating, which is 15 amps. So a protection must be provided to protect this module. So if we decide to provide a protection, there are the following statements that are guiding on string fuse selection. And we say that a string overcurrent protection device, that is OCPD, shall have the following current rating. That the device will be rated at ISC times 1.5. And this is a worst case in this case, as defined by ISC 62548. The other condition is that the conductor should have current carrying capacity of greater than the rating of the device, and the fuse or MCB rating also should be that the current rating of the fuse is less than that of the rating of the module reverse current. The minimum fuse rating voltage should be such that it is greater or equal to the open circuit voltage times the number of panels in that series times 1.15. So these 4 conditions are critical in selecting the fuse. And also we have that the device must be installed in both positive and negative cables for all strings. So not just one cable like the positive side alone, but all of the 2 cables, say the positive and the negative. Then the fuse must be of GPV type. This is in case where you're using a fuse and not the MCB. Again, let us explain that those conditions through a worked example. And in this case, we are being asked what is the size of string cable and string fuse if we have the following data that is provided here. So in this case, we are told that the VOC is 44.35, ISC is 8.48. Then we have the number of modules in series in the string is 18. The reverse current rating per string is, so we have this specification in this installation arrangements. We have the panels in series is 18 in that string. Then the reverse current per string is 15 amps. Then in this case the number of sub-arrays is just 1, and the number of parallel strings in the sub-array is 4. We want to find the string cable and the fuse rating for that particular string. And if we go further, we have the following conditions: that the fuse or MCB trip current should be greater or equal to 1.5 times ISC, and the fuse rating should be less than or equal to module reverse current. So from this statement, the string fuse rating should be equal to 1.5 times 8.48, which gives us 12.72. And the voltage, we check the voltage if it is less than 1000, which is a rating required for the overprotection device, this is 44.35 times 18, which gives us 918 volts, and this is less than 1000 volts required for the rating of the device. And as we move further from this equation, also that the fuse MCB rating should be less than the module reverse current rating, which is 15 amps. So we find that the chosen fuse we are going to take is 13 amps and 1000 volts rating and 2 pole. Now we need to check which cable is this that should have a current rating greater than this one for the fuse. So we move to this table to check conductor ampacity and find which cable is this that will give us this one. So this is our table 4.1a, and while discussing the problem, we have identified that we should have a cable which has a current rating greater than 13 amps, and this particular cable is going to be installed free in air. And we come like this, we find that the first cable is 20 amps, which of course is greater than 13 amps. Then we move to the left and we see that this cable rating is 1.5 amps. So we go back to our problem and finalize the solution to the problem. We come back to our problem and we have seen that from the table, the cable is 1.5 millimeter for current equal to 20 amps at 70 degrees. But what we say here is that the cable that you should have minimum for the string should not be less than 4 millimeter. In fact, some standards have it as big as 6 millimeter square. So when you have it like in this case 4 millimeter square, you need to now to check the voltage drop and see if it will satisfy the condition of being less than 2%. Now let us look at the current capacity of PV array cables. We have to define some conditions here, and these conditions are that if an array cable has an overcurrent protection device, then the array cable current rating IZ must be greater or equal to that of the protection device. So in mathematical terms, that is, we are saying the current rating for the conductor should be greater or equal to that of the overcurrent protection device. And this is so that the cable should not burn before the device trips. The other condition is that the current carrying capacity of an array cable without a fault current protection device is rated according to the following equation. So that we find that the current carrying capacity of the cable should be 1.25 times the array's short circuit current. So again, let us explain those conditions with an example. And in this case, we are told that a cable of type XLPE is to be buried from PV array to inverter housing 60 meters away. Find the cable rating and component rating in the system. So in this case also, we have been given these specifications. The module VOC is 37.2. The power is 250 watts. The IAC, the short circuit current, that is 8.87. The module reverse current protection is 15 amps. The voltage rating of the system is 1000 volts. So we are provided that in the arrangements, you will see this in figure 3, that the modules in series per string is 20. The strings in parallel in subarray is 4. The number of subarray is 3. So with those parameters, let us look at figure 3 so that we can comprehend further. So this is a figure, and what we see here is we have the 3 subarrays. This one, this is the second, and this is the third one. And the number of strings in parallel per each subarray are 1, 2, 3, 4. Then this is a disconnect. It is a combiner cum disconnect because it is combining the string cables, then giving us subarray cables, and we have 3 of them. Then we move from the level 1 combiner to the next level recombiner, and this one now combines the subarray cables and then gives us the DC inverter cable. In this arrangement, also we note that we have DC SPD between the level 2 combiner and the inverter, and we have been shown that the distance between the level 2 combiner and inverter is 60 meters, and that is why we are having these two SPD here. There's a requirement that if you have that distance, then you must have SPD close to the disconnect and another SPD close to the inverter. Then on the far right side we have the AC SPD as you move towards the electrical loads. So using this figure, let's try to understand the problem further. We move to the worked example because this is the best way to explain the requirements. This example is in 3 parts. So part 1 we are going to discuss the string cable rating, part 2 will be the array cable rating, and part 3 will be the inverter DC cable rating. So let's start with the string cable rating. So we are given conditions that the fuse or MCB trip current should be greater or equal to 1.5 times the ISC, and that the conductor current carrying capacity should be greater than that of the overcurrent protection device, and that the fuse rating also should be less than or equal to module reverse current rating, and that the voltage should be greater or equal to VOC times M times 1.15, where M is the number of modules in series in that string. These are the factors that we've been given here: 8.87 for the ISC, and IRC is equal to 15. So the trip current in this case for the protection device is given by that equation there, and we have applied it here, and this gives us 13.3 amps. And the voltage check for the system is the VOC times the number of modules in series times 1.55. This gives us 855.6, which is less than 1000 system voltage, and that is okay. The chosen MCB has a rating of 13 amps, and we are doing this because we are seeing that 13 amps is slightly less than 13.3, but this is because the next fuse is 16 amps. You are likely to get other manufacturers making fuses or MCBs which are outside the standard ratings that we had shown before. So in this particular case, we've just settled for the 13 amps. So moving further with our problem, we are told also the string conductor ampacity should be such that it is greater or equal to fuse rating. That is to say, the conductor current is greater or equal to the overcurrent protection device current rating. And using the overcurrent protection current rating, we move to the table 4.1a again to find the cable ampacity that is greater as per this equation. Looking at the table again, we find our cable, and we have calculated the overcurrent protection device rating at 13.3 amps, and again the cable that can safely carry that current is this one here, and if we move to check the size to the left is 1.5 millimeter square. So we have seen again from the table that the conductor is 1.5 millimeter square at 20 amps, and again for this string also we say that use a minimum of 4 millimeter square, and also check for 2% maximum voltage drop. Now let us do the part 2 of the problem, and that is the array cable rating. We see we have that the number of strings in parallel in the sub-array, there are 4, and the voltage check for this one is VOC times the number of modules in series times 1.15, and also that the array current is a sub-array current which is equal to the ISTC times the number of strings in the sub-array. The array cable current carrying capacity LZ should be greater or equal to the array sub-array current times 1.25, and this one is now 8.87 times 4 times 1.25. Remember, the array current is the IC times the number of strings in that subarray, and that is what gives us 8.87 times 4, and then now times 1.25, which is in this equation here. The current of the cable should be this amount. Then we need to check which cable is going to carry, has the capacity to carry this current. So we move back to the table 4.1a, looking for the cable that will carry 44.35 amps. So again, we move along this column, and we see that the nearest cable is 46 amps, and if we move to the left, we see that the cable size should be 6 millimeter square. So with that, let's move back to our problem. So we've seen that from the table 4.1a that the cable that can safely carry this one is 6 millimeter square. So we see that the subarray maximum fault current can be given by this equation here, which is the subarray current is equal to the number of strings in the subarray minus the faulty one times the number of subarrays times the IC of the system. And this gives us 4 strings minus 1 times the 3 subarrays times 8.87, the total current being 79.8 amps. It is stated that fuses are required where subarray maximum fault current, IAC subarray, is greater than the conductor can withstand. So in this case, we saw that our conductor was 44.35, or rather the rating for the conductor also is 46 amps. So we must have a protection device which will be lower than the rating for the current carrying capacity of the conductor. So the voltage for the system, if we check the voltage, is that we will get the voltage total running in the string as 855.6, and this is less than the 1000 voltage rating of the system. So this is okay. Now our selected MCB is 40 amps, 1000 volts, 2-pole, and this of course is less than our calculated cable carrying capacity, and therefore the cable is protected. So we move on to rate the main inverter DC cable, and this cable should be rated according to the following equation: that the current carrying capacity should be equal to the subarray currents times 1.25. That means the total subarray currents times 1.25, and the figure that we have here is 8.87 times 4 strings per subarray times 3 subarray times 1.25, and the total current is 133.05 amps. So this is a current that will be passing in that cable. We move on to the table again to locate the cable that is going to give us 33.05 amps, or which has a capacity to carry 133.05 amps. So this time we are looking at table 4.1b, which is a table for XLPE cables, and as per the problem, we were told that this cable is going to be buried directly, and the current calculated of 133.05 amps. If we move down along this line, we see that the cable above that figure is 144 amps. And if we move to the left, we see that the size of that cable is 25 millimeter square. So with that, let's move back to the problem. So from the table, we have seen that cable that can conduct this current is XLPE of 25 millimeter square, and we check for the voltage that it can withstand, and this is given by that equation there, and the voltage is 855.6, and this is less than 1000 volts of the system. So we are going to select an MCCB adjusted to 140 amps, and it should have 2-pole and rated at 1000 volts. So with that, we have concluded that process of the system component and cable rating. We thank you for having followed this presentation up to this point. We promise to bring more of this kind of presentations, and please subscribe to our channel. Thank you once again.